Okay, here's Edexcel 2017 AS Paper 1. Which of the following is not a vector quantity? Acceleration, definitely. Distance, no, because displacement is the vector version of that. Momentum and velocity both have direction, so they are vectors. Which of the following can be used to determine the magnitude of velocity? Area under an acceleration time graph. That should do, because if we're finding the area of a graph that's acceleration against time, then the area is going to be acceleration times time. So that should give us velocity. 3. A small plastic bead is released below the surface of water and rises towards the surface. Which diagram correctly represents the direction and relative magnitude of the forces? So if it rises at constant velocity, then we know that the forces must be balanced. So it can't be B because these two arrows are the same size as U, so the downward force would be bigger. Opposite with D, so we can discount those two already. But if it's going upwards, then we know that drag is pulling in the downwards direction. It's not pulling in the upwards direction, so it's going to be C. 4. A hairdryer is used for 3 minutes. The operating current is 6 amps. What charge flows in this time? We know that current is charge divided by time, or Q equals IT. So Q is equal to 6 times 3, but it needs to be in seconds, so times that by 60. We can already see that it's not going to be any of these three, they're too small. It's going to be D without even doing the calculation. 5. A student is deriving an equation for the total resistance of resistors in series. She writes the following steps but does not justify them. What a loser. Which step is justified using conservation of charge? Well, we know that in a series circuit where we have resistors, we know that the current has to be the same all of the way round. We can't have some charge flowing faster than other charge in the circuit because it's just one big loop. And also we must have the same amount of charge passing each point per second. So it looks like it's going to be step 4 because that is saying that current is the same all the way around. 6. A ball is kicked, giving it an initial velocity v and an angle of 35 to the vertical. So that's 35 degrees there. The ball remains in the air for a time t. Which of the following gives the distance traveled over the ground? Okay, so we want to find out just how far it goes by the time it comes back to the bottom. We know that this distance here is going to be horizontal speed times the time. So we know it's not going to be b or d because that's divided by time. Question is this velocity equal to v cos 35 or v sine 35? Well, if you haven't seen my easy vectors trick video, then I highly recommend having a look at that because it makes it much easier than faffing around with triangles, etc. But we're looking for the horizontal. That means that we're going from the velocity away from the 35. Turn away from your sin, turn away from your sine. So if we're going from here to here, that's going to be sine 35. It is C. 7. A series circuit consists of two resistors with resistances R1, R2. Which of the following gives the potential difference across the resistor with R2? Well, we know that when we have resistors in series, the bigger resistor gets the bigger share of the total voltage. So what we can say is this: V over V total equals R over R total. And V total being this right now, so V total. So putting this over the other side, we end up with a voltage that's equal to the resistance of the resistor times the total voltage divided by the total resistance. Obviously this is going to be R1 plus R2. So we know it's not going to be A, we know it's not going to be B, but we're looking for the potential difference across resistor R2, and so it has to be R2 on top. It's going to be D. Question 8. A light-dependent resistor and a negative temperature coefficient thermistor, why can't they just say LDR and thermistor, are connected in series. Which of the following combinations of illumination and temperature will result in the highest combined resistance? Okay, so we have this, and we have this. So we want a high resistance for the LDR. A high resistance is when we have low light, because when you have high light, it gives the electrons enough energy to start moving, to start conducting and move into the conduction band. So that means that we're looking for dark, so it can't be light. And here we are looking for a high resistance, and it's the same thing. We're looking for cold, because when the temperature increases, that means that, again, the electrons have enough energy to conduct. So it's going to be dark and cold. Number 9, a torch uses a 1.5 volts dry cell. Over time, the light intensity produced by the torch decreases as the cell goes flat. Student sets up the circuit, yada yada. Explain why the voltmeter reading will not be the EMF of the cell. And this is to do with internal resistance, isn't it? Because we can think of the battery or the cell having its own little resistor in there. Due to the internal resistance of the cell, some of the EMF is lost inside it. Therefore, bulb not have a PD equal to the EMF across it. Student B correctly determined the EMF of the unused cell as 1.63 volts and its internal resistance as 1.15 ohms. He repeated this after the cell had been used for several weeks. Voltmeter, then the reading was 1.36 volts. A bulb of resistance 5.92 ohms was then connected across the used cell and the reading fell to 0.84 volts. Student A suggests that the cell goes flat as it is used because the EMF decreases. Student B suggests it is because the internal resistance increases. Determine whether either student is correct about the changes in the cell as it goes flat. Okay, so we have the EMF and internal resistance to begin with, and we're being asked to find out the EMF and internal resistance afterwards as well. So if the voltmeter was connected directly across the cell, then that means that this is our EMF. So EMF equals 1.36 volts. So it has decreased from 1.63. Therefore, A is correct. However, we also need to see if B is correct. So bulb of resistance that, and we have the PD across it as that. So our equation is EMF is equal to IR plus IR. We can factorize that as IR plus R. And we're looking for the internal resistance. So what do we know? We know the EMF and we know the resistance of the resistor, but we don't know the current across it, but we can figure that out obviously because V equals IR, current is equal to the PD for the lamp, that is 0.84 divided by 5.92, that gives us a current of 0.14 amps. So all we then have to do is rearrange this to find the internal resistance. So let's just take our EMF and divide that by the current first of all. We end up with R plus R. Therefore, the internal resistance is going to be equal to the EMF divided by the current minus the resistance of the lamp. And that is equal to 1.36 over 0.14 minus 5.92 equals, then take away 5.92. That gives us an internal resistance of 3.79 ohms. Therefore, R has increased. B is also right. Number 10, the photograph showed two types of caliper being used in turn to measure the diameter of an iron rod. State the resolution of each of the calipers and compare their use for measuring the diameter of the rod. State the resolution of each of the calipers and compare their use for measuring the diameter of the rod. Well, the resolution of caliper 1, well, it can go to 0.01 of a millimeter. Resolution of 2, it doesn't go to quite that precision, so it's just 0.1 millimeter. So there's a couple of things we can say here. Percentage uncertainty in 1 is less. We can say it's more precise. However, this amount of precision is not necessary for measuring a relatively thick rod. And we can say actually that the variation in diameter of the rod is going to be more than 0.01 millimeter. So it would not take much variation in the diameter of the rod to change it from 12.17 millimeters to 12.18 or 12.16 millimeters. But that doesn't make a big difference in the end. This caliper would be fine for the job. B. The value obtained from caliper 2 was used to determine the cross-sectional area of the rod, and the electrical properties of the rod were investigated. Calculate the drift velocity of the charge carriers in the rod when the current is 1.9 amps. Diameter of the rod is that. Charge carrier density is that. So first things first, we need to find the cross-sectional area, and that is equal to pi r squared. But because we have diameter, let's go for pi d squared over 4. So that is pi times 12.2 times 10 to the minus 3 squared divided by 4. That gives me 1.17 times 10 to the minus 4 meters squared. And we know that current is equal to charge carrier density or electron density times the cross-sectional area times the drift velocity times the charge of said electrons. We're looking for drift velocity. So that means that V is going to be I over N A Q. So it's going to be 1.9 over 1.7 times 10 to the 29 times the cross-sectional area times charge of an electron, 1.6 times 10 minus 19. So I'm going to do the bottom bit first, just to make sure that I don't make any mistakes. And we have a drift velocity of 5.97. I guess if that was the 2 sig figs, I should probably put 6.0 times 10 to the minus 7 meters per second. Number 11, a motorist received a speeding penalty notice from the police for a short journey along 120 meters of road. The car's specification states that the minimum time for the car to accelerate from 0 to 60 miles per hour is 9.5 seconds. Show that the maximum value for the average acceleration of the car over 9.5 seconds is about 3 meters per second squared. 60 miles an hour, first thing we want to do is change that into meters per second. So 60 miles per hour, if we multiply that by 1,600, that gives us meters per hour, but we're looking for meters per second, so we need to divide by 3,600 to get it to meters per second. So that's 60 times 16 divided by 36 because the zeros cancel, and we end up with a speed of 26.7 meters per second. So we're being asked to find the acceleration. Acceleration is change of velocity over time, but it's going from 0 to 26.7, so we can just say 26.7 divided by 9.5, and we end up with an acceleration of 2.8. Let's go to 2 sig figs, meters per second squared. B. The police recorded a maximum speed for the car of 20 meters per second. The motorist knows that the speed of the start and the end of the journey was 0. Assume that the car had constant positive acceleration equal to the value in part A for the first 60 meters of the journey, constant negative acceleration of the same magnitude for the final 60 meters of the journey. Okay, so this is a SUVAC question. So we know that the distance is 60 meters because we're looking for the speed at the end of the acceleration. We know that the initial speed is 0. Final speed we're looking for acceleration is 2.8. So we're looking for an equation that doesn't have t. That's v squared equals u squared plus 2as. We don't need to rearrange it. U is 0, so we just end up with v equals the square root of 2as, which is the square root of 2 times 2.8 times 60. Square root of that, and we end up with 18.3 meters per second. So they recorded 20 meters per second. It is lower than police value, so it should be challenged. Bloomin' Popo and their dodgy speed cameras. Last bit, C. Explain why the assumptions about the acceleration in B might not be correct in practice. Max acceleration would only occur with no air resistance. But there's another thing that we can say, and that is that because it said that assume that it had the constant negative acceleration of the same magnitude, that's implying that you can't brake faster than you can accelerate. But we know that's not true. Bike can brake, decelerate, faster rate compared to acceleration. Bit of a weird question, that one. Tricky to get that second bit, maybe. 12. A student investigates how the efficiency of an electric motor being used to raise a load varies with the weight of the load. Time taken for the motor to lift a load from the floor to the maximum height was measured using a stopwatch. Load was varied by any weight, each marked 1 Newton. Spreadsheet shows the results and calculation. Explain how the value in cell F4 has been determined using the results obtained. So F4, we are looking at this row here. We're looking at this. Okay, first things first, we're looking for the work done. Work done by motor on weight. We know that that is equal to FD, force times distance. So that is 4 times 0.825 meters. It's the same throughout. And that is 3.3 joules. However, the input energy into the motor can be calculated using the current and the potential difference and the time. We know that power is VI, and so energy is VI times T. So that is equal to 4.3 times 2.1 times 2.19 seconds, 19.8 joules. So there's the energy out, there's the total energy in, therefore efficiency is equal to the bit divided by the lot. Don't ever write that in your exam though. So we're looking for 3.3 divided by 19.8, sure enough, that gives us 0.17, which is the same as their value. B, the student uses the spreadsheet to plot a graph. The student concludes that the efficiency of the motor increases with the weight of the load up to a maximum when the load is 6 newtons. Criticize the student's investigation and conclusions. So, first things first, the investigation. We are involving a time and a stop clock, and the times are relatively short. And sure, the resolution of the stopwatch might be okay, but there is reaction time involved, so it can affect the accuracy. What else don't they do? No repeats carried out. And we can see this like general shape, but we can see that there's an anomaly there. Anomaly at, well, that's at 5 newtons. It's not addressed, it's not acknowledged. Definitely should be, probably should have repeated. We are going up in 1 newton at a time. We could do with some results in between as well. Could increase weights in interval of 0.5 newtons. From graph, we can't really obtain the maximum, can we? And the conclusion as well just says that the efficiency of the motor increases with the weight up to a maximum when the load is that. So it's saying, yeah, it goes up to the maximum here, but then conveniently forgets about the rest of the results. So we can say that the conclusion ignores decrease in efficiency above 6 newtons. We can also see that the current is changing and the PD is changing as well. So should have controlled I or V2. 13. A gardener uses a trolley to move a paving stone. Force meter was attached to the handle of the trolley. The gardener recorded the following measurements when the trolley was at rest in the position shown in the diagram. So the length of the trolley is 97 centimeters, so let's go with 0.97 meters. Force on the handle is 50 newtons, and we have the mass of the trolley and the paving stone is 18.5 kilograms. So let's draw the weight coming from there, shall we say. So mg, pull it down. Determine the distance of the center of gravity of the loaded trolley from the wheel. So we are looking for this distance here. So even though the 50 newtons is not acting perpendicularly to the distances here, that's okay because actually mg is doing the exact same. So we could faff around with angles. We can say that that is the angle cos theta and then the angle cos theta as well, but actually they just cancel each other out. So what we can say is mg times d, that's force times distance, that's the moment due to the weight, is equal to 50 times 0.97. All we then have to do is rearrange it. So that means that D is 50 times 0.97, then we divide by mg, so that's 18.5 times 9.8. That gives us a distance of 0.27 meters. The gardener then pulled the trolley and measured the applied force when the trolley was moving. Now putting at an angle, the direction of the applied force is 25 degrees to the vertical. Calculate the magnitude of the applied force. Assume that the magnitude of the vertical component of the force remains at 50 newtons. Okay, so we're looking at for this force, but we know that the vertical component of that is still 50 newtons. So we know that the force is going to be bigger than the 50 newtons because the 50 newtons is a component. F is the resultant force. So we're going to be dividing by cos or sine. So F is equal to 50 divided by cos or sine 25. Question is it cos or is it sine? Again, if you don't know where I'm getting this from, have a look at my easy vectors trick video, but we are turning through the angle, and so that's going to be cos. It gives us 55 newtons. The gardener continues to walk and pulls the trolley a distance of 15 meters in a time of 4.2 seconds. Calculate the power developed while pulling the trolley. So we know that power is energy divided by time, or work done divided by time. And work done is force times distance. So we're looking for Fd over T. But we are looking for the horizontal force. So we're looking for that FH, horizontal force. So we can use 50 newtons or we can use a 55 newtons. It doesn't matter. I'm going to use a 55 newtons. I'm turning away from the 25. So I'm going to say that is 55 sine 25 because I know it has to be smaller. So I times by sine times 15 meters divided by 4.2. That is 83 watts. 14. The graph shows how the current through a filament bulb varies with the potential difference across the bulb. A. Determine the resistance of the filament bulb when the PD is 7 volts. So when the PD is 7 volts, we are looking at that. And so that is a current of 1 4.44 amps. And we know that V equals IR, therefore resistance is V over I, which is going to be 7 divided by 1.44, and that is 4.9 ohms. B, sketch a graph of resistance against potential difference for the filament bulb over the range 0 volts to 7 volts. So we said that when the PD is 7 volts, the resistance is 4.9 ohms. So we can put it across there, nice and easy to begin with. And we know that as the PD gets higher, then the current increases, so that means that the resistance increases as well. So we are going to be coming down. But is it going to start at 0? Well, no, it's not, because we're not going to have 0 resistance. That's a bit of a tricky question, that one. Explain the variation of resistance with potential difference for the filament bulb in terms of particle behavior. So, as PD increases, the current also increases, resulting in electrons flowing through filament at a greater rate. These collide with metallic ions and transfer energy to them, causing them to vibrate more. This results in electrons colliding with ions even more often. Number 15. Solar sails are a form of propulsion for spacecraft. The sail is made of a thin sheet of reflective material. When photons of light from the sun reflect from the material, a force is exerted on the sail. The photons reflect with the momentum equal to their initial momentum, but in the opposite direction. Show that a single photon of frequency 1.5 times 10 to the 15 Hz has a momentum of about 3 times 10 to the minus 27 Newton seconds. So we know that wavelength, the Broglie wavelength, is equal to h over p, p being momentum. So therefore, P is h over lambda. Lambda is V over F, so if we're dividing by V over F, that means that we are timesing by F over V. So that is Planck's constant times the frequency divided by the speed of light. Sure enough, if we treat photons as actual particles, they don't have mass, but they technically still have momentum, then we end up with that. Hence determine the momentum transferred to the solar sail by this photon. If it reflects, the change in momentum is going to be this times 2, so it's 6.6 times 10 to the minus 27 Newton seconds. An alternative method of producing a momentum change is being investigated. Researchers have suggested that larger changes in momentum could be produced by directing laser light at graphene oxide. Electrons are emitted from the graphene oxide surface, resulting in a force being exerted on the graphene oxide in the opposite direction. A researcher has suggested that one possible mechanism for the emission of the electrons is the photoelectric effect. Okay, show that the maximum velocity for a photoelectron emitted after absorption of a photon of light frequency. That is about that. Okay, so lots and lots of words, but we're looking for photoelectric effect. E equals, that is EK max, equals HF minus phi. So that is 6.63 times 10 to the minus 34 times the frequency, which is 1.5 again, times 10 to the 15. Take away the work function, 6.7 times 10 to the minus 19. So that gives us a kinetic energy of 3.2 times 10 to the minus 19 joules, but we are looking for speed. This is equal to half mv squared, so therefore v squared is equal to 3.2 times 10 to the minus 19 times 2, taking the half over to the other side, and then divide that by the mass, which is 9.1 times 10 to the minus 31. Square root all that to get the speed. Let's see what that is. So times that by 2, divide that by 9.1 times 10 to the minus 31, square root the answer, and that gives us 8.4 times 10 to the 5 meters per second. Hence calculate the momentum of the photoelectron. Easy. 8.4 times 10 to the 5, that's the speed, times 9.1 times 10 to the minus 31. How this is 2 marks, I will never know. That is 7.7 times 10 to the minus 25 Newton seconds. C, explain whether the suggestion in B that larger changes in momentum could be produced by directing laser light at the graphene oxide is true. Let's have a look. We have minus 27 over here. We have minus 25 over here. So the statement is correct, as change in momentum, also known as impulse, is greater than that of photon. And we've talked about the photoelectron, but because the photoelectron is going off in that direction, that means that the graphene oxide is going to go in that direction. Therefore, change in momentum of graphene oxide is greater as it is equal to that of electron. There we go. 16. A school's dynamic trolley has a plunger attached to a spring. When the plunger is pushed in, the spring is compressed. When the plunger is released, it is pushed back out by the spring. Student investigates the spring to determine whether it obeys Hooke's law in compression. Trolley was placed vertically on a scale and weights were added and turned on top of the plunger. Okay, there we go. The results were recorded in the table. Use the results to plot a graph of weight against compression. You may use the additional column for your process data. So we don't want the position, we want the extension. Let's keep it in centimeters, why not? So this is going to be 0, but then if it has moved from 37.3 to 37, then that means that we have moved 0.3. So we're going to be taking the numbers away from the initial position, 37.3, every single time. And let's plot it. Student concluded that the spring obeys Hooke's law with a spring constant of about 600 newtons per meter. Determine whether the student's conclusion is justified. Let's pick any point on the line of best fits here. Let's pick a nice number. Let's go with this one. And so that is 1.5 centimeters and it is 8.2. So F equals Kx. So therefore K is F divided by X, or delta L, whatever you want to call it. And so that is 8.2 divided by, well, 0.015 because it needs to be in newtons per meter. And it's about 547 newtons per meter. Now the mark scheme says that it should be about 568, which shows that actually my line of best fit should probably be a little bit more like that. I should probably invest in a proper ruler. But if this was the actual gradient, then 600 to 1 sig fig. So correct. Also, does it obey Hooke's law? Does obey Hooke's law, as F is proportional to X. Now the trolley was adapted by placing a tube around the plunger so that it could be used to launch marbles. How fine a marble was placed in the tube while the plunger was depressed. While the plunger was released, it launched the marble. Determine the maximum possible launch velocity of the marble when the spring is compressed by 5.4 centimeters. Spring constant is that. Mass of the marble is that. Mass of the plunger is that. So energy, potential energy in a spring. Elastic potential energy is half kx squared, and we know that if that's all being transferred to the kinetic energy, then that's going to be equal to half mv squared. So halves cancel, and so we end up with kx squared equals mv squared. We are looking for v squared, so we take kx squared divided by m, get rid of the square root the whole lot, so there's going to be 610 times 0.054, because the spring constant is in newtons per meter. This needs to be in meters as well. That's going to be squared divided by the mass of plunger and the mass together. So there's going to be 39.5 grams, but that does need to be in kilograms. So I'm going to say times 10 to the minus 3 and square root all of that. And that gives us 6.7 meters per second. Finally, the launch velocity was measured using a light gauge and a data logger. This produced a smaller value for the launch velocity than calculated in B. Give a reason why the method produced a smaller value for the launch velocity. Well, first things first is that it was being pushed upwards, so marble loses KE as it gains GPE. And there's another thing we can say is that spring also gains some of the energy. So that's it. I hope you found this helpful. If you did, then please make sure you leave a like. And if you want to go on to paper 2, then click the card and I'll see you there. Bye for now.